Let's take a look at the relationships between the big four motion variables. We have position, displacement, velocity, and acceleration. Except this I want to look at it from a graphing point of view. Now, if you recall, velocity, for example, is the change in position over the change in time. Well, that should look very familiar to you. If you have an XY plot, and I wanted to find the slope at a particular point here, slope is rise over run, or in other words, the slope is the change in y over the change in x. So if I take 2 points on a straight line here, it is the rise, the change in the y values divided by the change in the x values. So that means that if I have a position versus time graph and I want to find the velocity, well, I just do rise over run. That is the change in position, and that is the change in time. And so the velocity is just the slope of position versus time. Now, you notice that I'm using slope. I'm using a dollar sign here. And typically in math class, they use m for slope, but we also use m for meters. We use m for mass. And frankly, m is just used already too much at this point in the course, or soon will be. And so I don't want to use s because that also can get confusing. That's why I have the dollar sign. So that's my symbol I'm using for slope. Notice also acceleration is the change in velocity over the change in time. And so that means that if I have a velocity versus time graph and it is a straight line, well, that's my change in velocity between those 2 points, and that is my change in time. And so if I take rise divided by run, I get acceleration. So acceleration is slope of velocity versus time. Now, I did have the displacement right here, and so displacement is where an object is relative to the starting point, and position is where an object is relative to the origin. So if this is indeed the starting point right here in position, well, I can easily make a displacement versus time graph by just shifting everything to my origin here. So it would look like that. So in essence, I basically shifted this down to get to this graph. So if I start at my starting point, then my displacement graph starts at 0 here, and the slope is still the velocity. So this is also the slope of either one of these. So the difference between this first time and this first time is just basically the starting point. So if I'm going in this direction right here, I'm going to sort of lump those two together. So if I'm going down, then I'm basically taking the slope. So the slope of this first time is that, the slope of that first time is that, the slope of that first time is jerk, and then snap, crackle, pop. Now going the other direction, now with calculus it becomes a little bit smoother, but without calculus we do need to think about it a little bit more. So I have velocity here versus time, and so my velocity is increasing as I go. And I want to take a look at the area underneath it. So if this is, say, meters per second, and this is seconds, well, my area here, well, let's break it up into parts. This is some initial velocity here, and this is some final velocity. And this is some time interval, t. So my area here is the area of a triangle plus the area of a rectangle. So my rectangle here is base times height. So this is vi, that's my height, times time. My triangle here is 1/2 times my base, which is time, times my height, which is vf minus vi. So my total area is this. If I think about units, this would have units of meters per second times seconds, or meters. This would also have units of meters per second times seconds. I'm saying meters per second times second. The seconds would cancel out, and I'm left with meters. Put it over 1 if you need. So this has units of meters, so it gives some indication that we are dealing with some sort of either position or change in position, but let's take it a little bit farther. So this is the area underneath my curve here. And I say curve, that's just generic math term. It is a straight line at this point. I am assuming constant acceleration. So slope is constant. Let's write that out. Slope is constant. Therefore, acceleration is constant. So my area for this graph is VIT plus 1/2, well, that times t. Well, let's think about, I have constant acceleration, so Vf minus Vi is equal to a times t. If we divide both sides by time, we have basically the definition of acceleration. So time times, well, that's acceleration times time. So this becomes VIT plus 1/2 AT squared, which is, as we derived in the cake formula, or will derive in the cake formula, depends upon which one you do first, you end up with this. And so the area underneath my velocity versus time graph is displacement, or change in position. We can go through a similar argument for acceleration. And so what we end up with in the end is, if I write down my big four again, and again, lumping those together, and I only did it on one side for a reason, velocity and acceleration. So if reverse time, reverse time, reverse time. So if I'm going in this direction, slope. So to get from here to here, I take the slope. To get from here to here, I take the slope. If I go area underneath, I'm going in that direction. The area underneath this technically is not velocity versus time. Technically area underneath here is the change in velocity. Area underneath velocity versus time is the change in position, which is why I didn't lump them together on the right-hand side there. So slope takes you down, area takes you up. And recognize it is change in velocity and change in position, or otherwise known as displacement, when you're doing the area. Now, if you're dealing with a curve, if this is my velocity versus time, then when you're finding the slope of a curve, you basically find the slope of a tangent line. And a tangent line skims a curve at that one point. And so that would be tangent to this point right here. And so the slope, the acceleration at this point, since I'm doing a slope of velocity versus time, my acceleration is just the slope of that tangent line. So it's a positive slope there, so my acceleration is positive. Acceleration is positive. At this point right here, my tangent line skims at that one point. I find rise over run, and so my acceleration here is less than 0 because that's a negative slope. And at this point right here, acceleration is 0 because my slope of my tangent line is 0. So from this, I can sort of piece together acceleration versus time. I know that at this point right here, my acceleration is 0. I know at this point right here, my acceleration is 0, and it looks like I sort of peak right there, so my acceleration is 0 or very close to it. It's positive in this range right here. Starts out steep, becomes less steep, and so my acceleration does something like this. I know it becomes more and more negative, and then becomes less negative, and so it also has to get back to 0 at that point. Let me put my t over here. And then it's 0 at that point, and then it becomes more positive, not as steep as it is over here, so it's not going to come up as far, but it does start heading back down to 0. So whether that hits 0 or is just close to 0, that's partly a judgment call there for this particular graph. And so that's what my acceleration versus time graph would look like. Something like that. This is a crude sketch. I'm not doing any numbers here, so it's, ballpark. Now, if I went the other direction and went and do displacement versus time, so let me just draw my velocity versus time graph again here, at least somewhat of a, kind of looks like that. And so remember that the area underneath is my displacement versus time, so displacement versus time. Now, in this case, my velocity is positive the entire time, so displacement is never going to be negative, assuming I start at 0. Let's actually connect it up there. So displacement starts at 0. Now I start off here, but I start slowing down. Now remember that this is the point when my velocity is the greatest, which means this is the point in which my slope of my displacement graph will be the steepest. So the slope starts out low, the slope becomes higher. So it starts out low, becomes higher. At this point right here, my slope is the steepest. And then my slope starts to drop off. At this point right here, that is when it becomes the least steep in this localized area. Then it becomes steeper again because my slope is increasing, therefore my velocity is increasing, therefore my slope should increase, and then it sort of plateaus again. So I started up there for some reason. It actually, you know what? What I'm going to do is I'm going to get rid of that line right there and make that 0. Just put 0 over there, time there. That's slightly better. Now position time, there's not enough information in the graph right here. Position time is just going to basically shift this one way or the other depending upon what the initial position is. So I have velocity versus time. Say that's what my velocity versus time graph looks like. Acceleration versus time is relatively simple. Remember, this is the slope of that. And so at this point right here, my slope is 0. So my acceleration is 0. This is where my slope is 0 again, and my slope is, let's go ahead and make it 0. Level that off. So those are the 3 points right there where I know the slope is 0 because the tangent line is 0 at those points. And in this first region, my slope is positive, but becomes less positive. So my acceleration starts out positive and then becomes less positive. Then at this point, it crosses into negative. Now it gets more and more negative and then less negative. So it's most negative at somewhere around here. And then at that point, it starts to become more positive. Looks like it sort of levels off there. So it becomes more positive, levels off a little bit, and then something like that. So it's a judgment call. This little bit right here was not originally intended, but as I looked at this graph here, it sort of flattens out just a little bit. And so that's my acceleration versus time graph. It is a crude sketch, of course. If I look at displacement versus time, it's the area underneath. Now I start off in the negative direction, I then go in the positive direction, then I'm in the negative direction again. So I start out in the negative direction. I'm starting at 0 here, and I'm in the negative direction, and I start out with a bigger negative number, and then it becomes 0 here. Remember, 0, this is the slope of that graph, and so this is where it levels off. So let's actually sort of put some thin lines here. So it starts out negative and then levels off. So my slope starts out negative and then levels off. Sort of thinking something like that. Then my slope is positive, so that's the when it starts going around this way. This point right here, when the velocity is maximum, is when I have my steepest point. Now the question is, where am I going to cross back over here? Well, think about the area here. This area takes up that much space, and so it's going to be roughly somewhere around there is where it's going to cross. Because this is much positive area as that's negative area. You know, it is a crude estimate with an actual equation and some calculus or a spreadsheet or patience, you can figure it out yourself. But then it becomes steepest here. And then it starts leveling off to 0 again. So sort of ran out of a little bit of space there. Then it's negative again. So my slope here is negative because my velocity is negative, and then it levels off again there. And then my velocity is positive, so my slope is positive Here my, again, velocity is at a peak here. And so my slope should be peaking at that point. So there's a crude, rough sketch of my displacement. When my velocity is negative, I'm going in the negative direction. When my velocity is negative here, I'm going in the negative direction, but I still stay on the positive side of my original position. Again, crude sketch. Point out a couple of places here. Where I'm speeding up. I'm speeding up from here to here. I'm speeding up from here to here and speeding up from here to here. These regions right here are where I'm speeding up because I'm getting away from zero. Here I'm speeding up in the negative direction. There I'm speeding up in the positive direction. So that's speeding up in the negative direction. Notice in this region right here, my acceleration is negative and my velocity is negative. I'm speeding up. Here, so here my acceleration is positive. My velocity is positive. I'm speeding up. And here, acceleration positive, velocity is positive. I'm speeding up. On this graph right here, where am I speeding up? Well, I'd have to know what my initial velocity is to know where I'm speeding up. So if I gave you this one, I'd have to give you this bit of information right here so that you could then plot that and then figure out where it's speeding up and slowing down. Because if I just gave you that, there's not enough information to know. Because if my initial velocity were sufficiently negative to the point where it never becomes positive, then I'm speeding up in this region right here. But if I closer to at rest, so this would be at rest. So if I'm closer to at rest, then I'm obviously speeding up in different regions here. So in this case right here, I'm speeding up. So in this situation, I'm speeding up here, here, and here. And on this graph right here, this is when I am at rest. These spots right here are when I am not moving. That's when I'm turning around. So I speed up as long as my slope is getting steeper. So that's basically there. And then here, and then there. So those are the places I'm speeding up on this graph.